Okay. So remember that for the last few days we've been talking about the diffusion equation. Which looks like an equation of the form delta by delta t of some quantity p of r in t equal to d del squared of p. Instead of p, sometimes I used rho of r and t, but really these were the same things. There were two problems that we tried to address. One is we said, imagine that there is some particle here which is diffusing around. We want to find out what is the probability of finding it at some later time t. Okay? So what we're interested in is the probability of finding the coordinate of the particle in some small distance or small volume around r at some later time t, given that we knew where it started off from. That was one set of questions. Then we said this was the same thing as looking at a whole bunch of particles here, which specified by some density rho of r at time t, and then asking how the density changed in time, which is why we use these two different types of notation. But in the examples that we use, typically they concentrated on looking at a single particle and asking what are the properties of the probability distribution of where the particle is at time t in terms of probability distribution over a coordinate r. Okay? So the interpretation is r is the distance from the starting point to the end point. It started off here. So technically speaking, this is p of r comma t given 0 comma 0. So the right way of saying is this is the probability of finding the particle in a small volume about a position r at time t, given that it started at the origin 0 at time t equal to 0. That's how one would say it in a more official manner. So then we said we derived an equation of this form, calling it a diffusion equation, and we had begun to write down solutions of the diffusion equation. But some of the main properties of this were that if I looked at the quantity r squared times p of r comma t given 0 comma 0, this quantity, which is the mean square displacement, sorry, let me just write it in a little different way, r squared times p of r 0 comma 0 integrated over all values that r can take. This is the average value of r squared, or the mean square displacement. And then we found that the mean square displacement squared, the mean square displacement was written in this form 6 times the diffusion constant times the time t. And this was in 3 dimensions. In general, the expression was twice the dimension times the diffusion constant times t. And then we use this to estimate various quantities. We won't use it to estimate the time that a small molecule, protein molecule, might take to diffuse a distance of order 1 micron, and also the time that it took to diffuse a distance of order the size of a typical test tube. Okay. We then said, let us solve this equation. In order to solve this equation, we need to specify where it is, at the probability of finding it at time t equal to 0. So that we said, let us assume that we start off with a condition that is a delta function condition, saying the probability density of finding it at any point x at time 0 was just given by this quantity delta of x. So this is the initial condition that I must apply as input to this. Then we figured out how to solve this question, and so we finally said that p of x comma t. I'm now going to switch for simplicity to one dimension just to make things simpler. This was 1 over 4 pi dt to the power 1/2 exponential of minus x squared divided by 4 times t times t. So this is a solution that says that at t equal to 0, I'm a delta function exactly around 0. At a little later time, this broadens and it looks like that. It's still symmetric between x going to minus x. So it's a function that's symmetric about 0. At a later time, it comes down here, and the fact that this comes down, I know from the fact that if I set x equal to 0, which is the value here, then I know that with time it comes down as 1 over t to the half, which means that this value must come down as time goes on further and further and further away. So this quantity, which is r squared average, is a measure of how broad this distribution is. Over here, what is the width of this distribution? Okay, so now we can do other things. For example, suppose we did not start off at 0, but we started off at some other point, say x0. How would we solve that? So now if you will remember, the way that enters is in the form of rho of k comma t is rho of k comma 0 e to the power minus d k squared times t. Okay? This is where the memory of that condition actually sits, in the rho of k comma 0. And if you remember how we derived it, we said rho of k comma 0 is obtained by taking rho of k was 1 over 2 pi integral minus infinity to infinity e to the power minus I k x times rho of x. This is the inverse Fourier transform with a factor of 1 over 2 pi. Okay. So this was essentially 1 over 2 pi. But now suppose rho of x, and we said rho of x was initially a delta function of x, in which case this came factor of 1 over 2 pi. But suppose it was not a delta function of x, but a delta function at some other point. For example, suppose it was a delta function at point x0. Then rho of k at t equal to 0 would then have the form 1 over 2 pi integral minus infinity to infinity e to the power minus I k x delta of x minus x0. So that's the peak, the delta function peak at some other point x0. So this would just be 1 over 2 pi e to the power minus I k times x0. That's all the change that would be. Because this delta function, wherever it sees x, it sets an x naught and puts an x naught over there. So that's what I would get. And then when I have to Fourier transform back to get rho of x comma t, this would then become 1 over 4 pi dt let me just write it again, 1 over 2 pi integral minus infinity to infinity dk e to the power I k x 1 over 2 pi e to the power minus I k x naught e to the power minus d k squared times t. This is just going back to real space from an expression like this, having substituted the form of rho k comma 0 as this one. Is that clear? So what we did was, you agree that this is the form that we described earlier. This is the result that we got when we took a Fourier transform. In terms of rho k comma 0, which is the initial condition, and this factor expression minus dk squared times t, we were able to write rho of k comma t. The next step is only taking rho of k comma t and going back to real space. To get rho from here, if I Fourier transform back, I get rho of x comma t by just Fourier transforming in the k. That's all I've essentially done here. This is the initial condition here. The rho of k comma 0 is a factor that sits here. This part is a factor that sits here. And this part is the Fourier transform that enables me to go from k space back to real space.
So,
do I have too many factors of 1 over 2 pi? I probably do, right? Yeah. I shouldn't have a factor of 1 over 2 pi.
X is the space domain.
X is the spatial domain.
K is the?
K is the Fourier domain or the wave vector domain. K is sometimes called a wave vector. You can also call it the Fourier domain. In this place, because X is space, then K is called a wave vector. But in general, you can go from time to frequency with any quantity. For example, it would be the Fourier and the inverse Fourier are pairs of each other. So T and omega would be pairs of each other. X and k would be pairs of each other when you Fourier transform back and forth.
Here time is in the both cases no change for the time.
There is no change for the time. This is only a Fourier transform in space, in Fourier space in this particular case. Okay. So now this is easy to.
Is that spatial frequency actually?
You can also call it spatial frequency. That's a slightly more uncommon usage, but it means the same thing as the angular frequency as far as the time. You can also call it a spatial frequency. You can also, but in usually the letter k is reserved for something called a wave vector. Okay. So now we can just write this as an integral minus infinity to infinity dk e to the power I k x minus x naught times e to the power minus b k squared times t. This is rho of x comma t. And now I can do this particular integral. But it's much easier for me to see that nothing here depends upon the value of x minus x naught. I could call it whatever it was. And remember, this is what turns up as exponential of minus x squared by 4 dt. Earlier this was just e to the power I k x, and that became an x squared here. So now it's x minus x naught, but that shouldn't make a difference to that answer as long as I substitute it correctly. So then the answer is rho of x comma t is 1 over square root of 4 pi dt exponential of minus x naught divided by 4 times d times t, with a square here. So what this means is that instead of broadening at the origin as we do it there, it now broadens about this point x naught. It begins to look like that as time goes on. It's just shifted it. Okay? And the other sort of slightly more technical way of remembering it is that shifting the argument of a function from 0 to x naught is like multiplying it by a phase factor, e to the I k x naught. That's a simple way of trying to remember what happens if I just move it. You just multiplies it by that simple factor there. So if I was transforming f of x and I made it f of x minus x naught, then I would just have the original Fourier transform that I had multiplied by e to the power minus I k x naught. Okay?
So it was shifted in the spatial domain.
It is now shifted only in the spatial domain. The time part remains the same. So instead of broadening about x equal to 0, it now broadens about x equal to x naught.
So then we have 1 by 2 by the previous step, second step. Rho of x is second step.
This one?
1 by 2.
Yeah. Exactly.
Why do you have
1 over 2 pi because I remembered it from. Okay. Suppose now instead of having a delta function signal there, I say I have some initial probability of finding the particle, and that probability may have looked like some complicated function that might have looked like that. So this is the density at position x at time t equal to 0 as a function of x. So instead of saying I know that it was a delta function at t equal to 0, I am saying it's some more general distribution at t equal to 0. And let me call this some function, say rho of x comma 0. How would I handle that? The answer is I would handle it pretty much exactly as I do it here. But from the rho of x comma 0, I would Fourier transform to get a rho of k comma 0. And if at some point earlier in my notation I put all the Fourier transforms as rho hats, that's technically the right thing to do so that you don't confuse this to be the same function in which I just substitute x and k. This is not. Anything with a k index inside is a different function, it's a Fourier transform. But if so, one way of being careful about that is just to put a hat wherever a k appears, just to emphasize the fact that it's a different function. Okay?
So even if there is no cap, it's okay.
If there is no cap, it's fine, except that you have to remember that if it has an argument that is k, it is a function, so Fourier refers to the Fourier transform. You should not say that, look, there is some variable here and I can substitute water because it's just a function of x, I can put anything I want into that. It's not the same function.
Just
It's
like
a, it's a
using the
pair.
capital F.
It's like using a capital F. It's just to say this is a different function and it has a different, so either you can use the same notation, but remember that the moment you see a k, it is different, has a different interpretation from the one in which you see an x. Okay? So as I said, this initial condition, if it's more general, turns up as rho hat of k comma 0. And now you have a slightly more complicated integral to do. You have to calculate the inverse Fourier transform of some general function here, rho hat of k comma 0, multiplied by the exponential minus dk squared times t. So let's just sort of ask, how does one deal with products of functions like that, and the Fourier transforms of products of functions? What do they actually mean? So let's just try an example of, just to sort of illustrate what I'm talking about. And that example is some case where I define a function, say capital F, a function of x, to be the following. It's an integral from minus infinity to infinity, some function small f of x times some function small g of x integrated over x. Let me just change this slightly. Let me say this is a function x prime, this is a function g x minus x prime and integrated over x prime. Okay. This is now, this is still, I'm integrating over x prime. So this quantity, this is some general function. I'm just writing, suppose I had a function f of x defined in this particular manner as an integral over all values x prime from minus infinity to infinity, the product of two functions in a particular way. This is a function of x prime times another function of x minus x prime. Because x prime is integrated over, this quantity can only depend upon x on the left hand side. Okay? And this looks like a slightly complicated way of writing it, but why this is advantageous to do that will become clear when we try and write this in Fourier space. So let us say we want to take the Fourier transform of this quantity f of x, and we also want to take the Fourier transform of this quantity that is inside this integral here. So let's just do that. Let's just say that f hat of k, the Fourier transform here, is minus infinity to infinity dx integral minus infinity to infinity f x prime g of x minus x prime d of x prime, and then I must multiply this by e to the power I times k times x, because this is how I Fourier transform a function that is a function of x. And here I must be a little careful about factors. I must put a factor 1 over 2 pi here and put a minus sign here, because this is technically an inverse transform. I want to get, I have f to k, k to f. Remember how we did it earlier? We said f of x was the integral minus infinity to infinity dk e to the power I k x f hat of k, which meant that f hat of k was 1 over 2 pi integral minus infinity to infinity dx e to the power minus I k x f capital F of x. That's essentially what I'm doing here. I'm going back to Fourier space from real space. Okay, is that clear? If it's not clear, you should tell me.
This e to the power minus I k term comes from the definition of f cap k, right?
That's right. So that comes from this factor here, e to the I k x. This is a function of x only, because I've integrated over x prime. I've just chosen to write it in this particular form. Okay. Now let me interchange these integrals. Let me write this as 1 over 2 pi integral d x prime then I can put f of x prime in here because this doesn't depend upon x. Then write this as integral minus infinity to infinity. So all these integrals are minus infinity to infinity of d x prime d of x, g of x minus x prime e to the power minus ik times x. Okay. Now what I am going to do here is I am going to multiply by a similar looking factor. Over here I am going to multiply by e to the power I k x prime, and over here I am going to multiply by e to the power minus I k x prime. Okay. This is just the same thing. This is just multiplying by 1.
Last step.
Yeah, I am just going to multiply by 1, which is e to the power I k x prime into e to the power minus I k times x prime. Okay.
What is where are the factors to be multiplied?
Before the second integration.
E to the power ik x prime.
Yeah, I am just going to write it in this form, e to the power I k x prime, e to the power minus I k x prime. I can just, as long as I put it before the x prime integral, I am fine. I am just basically multiplying by 1 because e to the power x into e to the power minus x is 1.
What happens to e to the power minus ikx?
That's still there. That's still there. I haven't fooled around with that.
But you are not written e to the power minus ikx prime yet.
I'm not. I've just said I'm going to multiply by this factor. Now we want to try and disentangle those factors, and I will just tell you how that's done. I'm going to write the first term as 1 over 2 pi integral minus infinity to infinity. I have a dx prime. I have f of x prime. I'm multiplying by e to the power minus ik times x prime. So I get rid of, I put one of these factors into this. And I take the other factor and I put it there. And I get integral minus infinity to infinity. What did I call that? I call that dx. G of x minus x prime exponential of I k times minus I k times x minus x prime. Is that correct? Okay. But now notice that I can always shift this variable whichever way I want, because it's just this variable x minus x prime. I can shift it for every value of x prime. I can just shift this because the integral goes from minus infinity to infinity. This integral doesn't care about the value of x prime. Okay. So this is just the Fourier transform g of k.
That's because what we get over the integral will be a function of x. It doesn't care about x prime.
That's right, because I can just define a new variable u, which is x minus x prime. Then dx is du. So this is gu times e to the power I k u, which is just a Fourier transform of that same function. It's just because that u is a dummy variable, I can change it. So just saying because the same variable appears here and here, I can always it's just the same integral all over again. If you want, we can write it in more steps, but you can just try. Suppose I have a variable u, which is x minus x prime. This is an integral over dx, so it doesn't care about the x prime at all. So du is the same as dx. So this integral, because x prime is finite, the integral doesn't care. It's still minus infinity to infinity. I have a du times a gu times e to the power minus ik times u. Now whether I call this u or x, it doesn't matter. It's just a dummy variable. So therefore, this is a gk. And over here you will see this is also the function f of k. It's a Fourier transform of the function f of x. And if I'm being really careful, I would put hats on all of these.
2 pi's.
And there's a factor 1 over 2 pi. So therefore, the Fourier transform f hat of k is just 1 over 2 pi times the product small f hat of k, small g hat of k. Alright. So this is just saying that suppose I ever land up in a situation where I have two functions of k whose Fourier transform I know are multiplied with each other, then the Fourier transform of this combined object is f hat of k, and the inverse Fourier transform of that is where this function originally came from. Okay. This way of writing it is called a convolution. And this is sometimes expressed as saying the Fourier transform of a convolution is a product of the Fourier transforms. That's all.
So actually 2 pi, it is 2 pi.
Sorry, too many people talking at the same time. Start. Yeah.
It is 2 pi into g hat.
Why did we get 2 pi into g hat?
I mean, for the inverse Fourier transform, you have a 1 by 2 pi outside. Sir, on top there, integration. Definition of inverse Fourier transform.
The right side.
Here?
You have a 1 by 2 pi outside. So
Cap.
top.
The right
The
hand side,
definition.
yeah, this one.
Yeah. So this 2 pi will come outside.
Because it's a cap.
Oh, because of the 2 pi. Okay. So you're saying that I should not have this. This is just directly.
You have 2 pi into that.
You have 2
2
pi.
pi
Sure.
from here, 2 pi from
All right. All I'm saying is that this f hat of k is related to. Oh, I understand what you're saying. You're saying that I should be more careful about the factors of 2 pi that I have. Yeah, let's sort that out. But the real point that I wanted to make was that apart from these factors of 2 pi and where they should be, which you can figure out, this is all the interesting k dependence is just the product of the k dependences of these two functions. Okay?
Because this cap and that cap are the same thing, right?
Yeah.
Convolution corresponds to multiplication.
No, it corresponds to an integration in a very particular, yeah, convolution in the real space. For example, f of x prime g of x minus x prime corresponds to the product of the Fourier transforms. So that's exactly what we were trying to do when we were looking at this problem where we had a general rho hat of k comma 0. We said rho hat of k comma 0 would multiply exponential of minus dk squared. So this factor might be g of x, this might g of k, this might be f of k. So the product of this is related to the convolution of these two functions as they actually were. So this would be a convolution of the initial density in reals, the rho of x0 times the function which is x minus x prime. Okay? So that I can actually write. So ignoring factors of 2 pi which we can always reinstate later, rho of x comma t is obtained by taking an integral over x prime, rho of x prime at time t equal to 0 into this factor of 1 over 4 pi dt to the power 1/2 e to the power minus x prime squared divided by 4 times d times t. And I have to be a little careful about which factors of phi, 2 pi enter there, but we can sort that out later.
Convolution is capital F times fx into capital F times g x minus x prime is equal into
Yeah.
capital F.
No, these are both small, these are the original functions f and g.
Yeah, but we have separated them here. Right?
We have separated them there, exactly. So this is the function that I said is this is the same situation that I had here when I said let me start with some general density here. Some general density at t equal to 0 has a Fourier transform which is rho hat of k comma 0, some function of k. This is what sits inside here. Okay, it's still multiplied by another function of k which is exponential minus dk squared t. So it's as though I was thinking of this particular part of it as rho hat of k comma 0, which is the same as what I might have called g of k. And this factor here will be what I might have called f of k. So this would be the inverse Fourier transform of the product of two functions to get to real space. The product of these two functions in K space is a convolution in real space, which is why I can write it in this form.
What the last sentence, the product of?
We had the product of these are two functions in K space. So they look like this result that we had here. For where did it go? Yeah, for this particular quantity here. The Fourier transform of the product of this, which we call some general function f hat of k, is related to the original way in which these functions appeared in real space, but in a very peculiar way, in the way of a convolution. But once I know that, I can just go back here and just write that answer down immediately. That answer says, take the density at the time t equal to 0, but multiply the function by something which is x minus x prime, because of the way the convolution is written, integral dx prime, f of x prime, g of x minus x prime. Okay. This is just a little technical, and we may not really use this, but it's good for you to see it at least once in a while. And the reason is just sort of thinking about what this is doing.
What does convolution mean physically? Like, how do I visualize it?
It's easy to sort of see what it's doing here. It's saying, suppose I have some initial distribution function that is like this, and I want to look at what it is at some later time t. So the density at so suppose, okay, so this is rho of x at time t equal to 0. It looks like this is a function of x. At some later time t, it might have looked like something like this. What I'm saying is that this function at some later time t has a contribution from every little piece of this function. This might contribute less because it has a further distance to go than this. Here, particles that are sitting in this part of the distribution don't have very much to go before they can sort of fill in this later distribution. So this is like a weight for densities at different points. This is the density at different points at time t equal to 0. This is the weight that it gives to the final distribution. So it's as though you're weighting this by a certain amount in order to get to that final state. So the technical, sometimes this is also called a Green's function. So this would be the Green's function for the diffusion problem. And the interpretation of this is very straightforward. It just says, given any arbitrary density, the Green's function is what tells you how much of the density moves forward and contributes to the later density at any time. That depends both on what time it's going to be, how much time later, as well as on what is the initial shape of this. Because stuff that is far away will contribute less to a particular point x. So thinking about the Green's function is often an intuitive and nice way of sometimes numerically tackling a problem or even making some analytic progress with that problem. Okay. So now let's just look at a few more uses of the diffusion equation in some other context. Remember that when we started off, we said let us write the diffusion equation in the form delta rho by delta t is minus del dot j. And we said that this had two uses. First of all, it expressed this behavior of the density in terms of a local conservation law. Okay, so that whatever density was inside any volume here could only leave or enter through the boundary of that volume. If I took the volume to be very large and said suppose this is a box and nothing can leave the box, then the total number of particles inside that box would be fixed. If I just asked what are the properties inside any sub-volume here, this number can only change if something leaves the boundaries. If nothing leaves the boundaries, then the number remains the same. So this says that locally, however small the volume is, the number inside is a conserved quantity. It can only change because particles leave through the boundaries of the system. It can't change because I'm allowed to remove particles from the bulk at random. So these conservation laws are very important, and we will see them later when we discuss the behavior of fluids and how biological fluids, just like ordinary fluids, can be described by equations. in this case a Navier-Stokes equation, and they will also express certain types of conservation laws. And that's important for us to remember. But right now we just have to remember the form that this equation here is called a continuity equation, and this just says that you cannot create or destroy. It's a local statement of the fact that you cannot create or destroy particles. Okay? You cannot create or destroy particles at all. That's what this equation says. If particle numbers change, they can only change because they are actually leaving the volume that you're considering. And that is only through the boundaries. They cannot change because of creation or destruction of particles inside that volume. That's an important point. And maybe I will give you a problem set that discusses some of this. So that they should not be, because this is an important relationship for us to work with. Then we said we can take the J, the expression for the normal expression for the current J is the density times the local velocity, rho times V. This is the current density. So it has a dimensions of a number per unit area per unit time. Okay. And we said this was a general expression for a current. Suppose we had some density of particles here and they were all moving with some velocity V, then rho times V would be the current, the number crossing per unit area in per unit time in a particular direction given by the velocity V. But if I put that into this diffusion equation, what I would get is there is some part to the current, let me call it the diffusive part, which looks like minus d times the gradient of the density. This is not the same as this. This assumes there is some net velocity which is moving the particles. Maybe they have a charge and I put an electric field outside them, all moving towards the electric field at some constant velocity. But this is V is the velocity. So suppose all these particles here, I have asked them to move with some velocity in this direction. That sets up a current, because if I put a little surface here and I ask how many are crossing this particular surface here, I can get that from the current. I just take the dot product of the normal to the surface, multiply by the area of the surface, that gives me the number crossing per unit time. Okay. But we had another expression for the current which came just from looking at the diffusion equation. Remember that the diffusion equation has the form delta by delta t, again in one dimension, rho of x comma t equal to t del squared of rho. If I write this as minus del dot j, then I have to write j itself as minus d times the gradient of rho. So del dot j would be minus d del dot gradient of rho, which is minus d del squared of rho, and the minus sign and the minus sign here would go away to give you a plus sign, and thus the old equation that we had. Okay. In general, the fact that I can have particles that are moving in the fixed velocity v, but I can also have them diffusing. So physically this might have been, here are particles here, and more or less they're moving in this direction, but maybe they're diffusing a little bit around those. So it might look a little bit like that. So on average, if I take a snapshot of it now and a little time later, these particles would have moved in this direction. There will be some net motion as a consequence of this velocity. But still it's not completely smoothly moving along a trajectory because it's also diffusing. So it's a combination of these two factors that are important. Okay. So the way one writes it is, one would write an equation of the form, here is how the density changes. This rho by delta t is minus del dot j, but now j has two paths, one from here and one from here. So I would write delta rho by delta t is minus del dot rho times the velocity v plus d times del squared of rho. So this is just the regular current term, which I call a systematic current, which might come from having some net velocity here, and this is a diffusive current that comes from diffusion. This equation here is called a drift diffusion equation. Okay. In fact, we can make things sometimes a little more simpler. If suppose V didn't depend upon space, then as far as this grad operator is concerned, it doesn't look at it at all, it's just a constant. So I can pull this factor out here and write delta rho by delta t is minus v dot the gradient acting upon rho plus d del squared acting upon rho. This is true only if v doesn't depend upon space. Otherwise, the more general expression is always true. What I have done is take the v out, and del dot rho times v, this is del dot scalar times a vector, that can be written in this particular form as v is constant. V dot the gradient acting upon rho. V dot gradient is, if v is Vx, Vy, Vz, and the gradient grad is x hat delta by delta x plus y hat delta by delta y plus z hat delta by delta z, then v dot grad, which we will see in some other form later, is just Vx delta by delta x plus Vy delta by delta y plus Vz delta by delta z. And this is now this is not a vector, it's just a scalar that acts upon rho. And I suggest that you check this, that this actually reduces to this. If v is a constant, it can always be written in this particular form.
That is the divergence.
This is it's called the gradient operator. It's a divergence only if it operates on a vector. A gradient operator can operate either on a scalar or a vector. If it operates on a scalar, such as density, this object gives me a vector. If it operates on a vector, such as a velocity, this gives me a divergence.
This d rho by dt is del dot product of the entire thing, or just rho v?
Where are you reading?
The d rho by dt.
Yeah.
So this is dot product of the
Velocity dot the gradient. In fact, maybe I can make the notation a little easier. Let me just call this C, so that it doesn't look like my V, like my gradient operator. Some velocity dot the gradient, and this is what I mean by velocity dot gradient. Okay, it's just Vx times delta by delta x plus Vy times delta by delta y plus Vz times delta by delta z, and this is an operator that must operate on some function to the right hand side.
right hand side is a scalar.
The right hand side is a scalar. It's a scalar here and it's a scalar here. There are no vector signs anywhere here.
And this d del square rho is also a scalar.
That's also a scalar. Everything here is a scalar. Del square is delta squared by delta x squared plus delta squared by delta y squared plus delta squared by delta z squared.
So I have a confusion in the notation. That is the dou by dou x of Vx plus?
No, Vx sits outside, because we said, remember that we said that the velocities are constant. That's the only way you can go from here to here. This is the most general way of writing it. We said the current has two paths. Here is a current. One is some systematic current, because there are velocities in the system, and there is a diffusive current which comes from diffusion. We said the systematic current had the form some velocity times the density. We said the diffusive current had the form minus d times the gradient of the density. Both of these are vectors. This is a vector in the direction of the local velocity. This is a vector in the direction of the gradient of rho. This is what helps you. Suppose you have a density gradient like this. This says that particles will move from higher density to lower density until this is sorted out. And that's what this really means. The diffusive current says if the current is large, density is larger here and density is less there, it will move from regions of larger density to regions of smaller density. So now this has two paths. One comes from here, one comes from here. This is always, if I take this and then now I write delta rho by delta t is minus del dot j, which is the same as minus del dot, the two paths to the j systematic and the j disorder. The first part, the del dot j systematic, would be del dot rho times c. The del dot j diffusive is del dot minus d grad rho, the minus sign outside again, That gives me d del squared of rho. Is that clear? I can simplify to this particular case only if the C is not a function of space. Otherwise, this is the right way of writing it. The del operator operates on Js as a whole, on rho of x and C, rho and C.
But you did not do that.
I didn't do that. I said, suppose C is a constant, then I can pull it out. Only in that case.
C is a constant.
Only if C is a constant does the gradient operator not act on the C.
If it's a function of time, you can't do that.
With a function of time, I can also do that if it's a constant. So put points in the same direction. Even if it changes sort of globally, I can still do that. Only this is only concerned about how it behaves as a function of space. Okay. Now, let's just look at this in one dimension, just to make a point. In one dimension, this equation, the drift diffusion equation, the dd equation, looks like delta rho by delta t equal to minus c delta by delta x of rho plus d delta squared by delta x squared of rho. This is the one-dimensional drift diffusion equation, and it differs from the diffusion equation by this extra term here. So now how does this change the results? So I'll just give you the final answer, and then we can discuss a little later maybe in the problem how to prove it. The answer is that the density, suppose I start off at the origin, the delta function at time t equal to 0, then the density at some later time t as a function of x is just 1 over 4 pi dt, you must be getting used to this by now, to the power 1/2 exponential of minus x minus ct the whole square divided by 4 times d times t. Okay? Let's see what this means. So now I have an additional factor of time entering upstairs which I didn't have. If c was 0, then this term would vanish altogether. This would be the old diffusion equation with the solution exponential of minus x squared divided by 4 dt. I didn't do it, we can do it later, but I didn't show you exactly how it's done. I just said, let me give you the final answer. From this you can easily get to that. And the reason, the way you do that is to make a change of variables to say one variable which is x prime, which is x minus ct, and t prime, which is t. You change the variable from t and x to x prime and t prime. You get an equation that looks like the diffusion equation. You write down the solution of that diffusion equation. Then you change your variable back to x minus ct, and then it finally looks like that. But more than that, I wanted you to look at what the interpretation of this was. This says, suppose here is my, at t equal to 0, I am here at my origin. At some later time t, say t1, I have moved here c by distance c times t1, and I have broadened slightly. At some later time c times t2, I have moved even further and I have broadened even further. At some later time c t3, I have broadened much more further and more. Each time the point of this maximum here is given by x equal to c times t. Because if notice that whenever I set x equal to ct, this quantity becomes the maximum value that it has. Okay? But as time goes on, the value that it has here is coming down, just as it did when it started off with 0, when it only broadened sitting at a point. So now it is drifting and it's diffusing, which is why it's called.
The starting point was impulse.
The starting point was impulse at t equal to 0. At some later time, the distribution function peaks at c times t. So if I look at some later time t1 greater than 0. At some even later time t2, this peaks now at c times t2. So the location of this peak here keeps on moving to the right. And I know exactly how it's moving because I know that if I set x equal to ct, that gives you the maximum value that it has.
Why do you say that the peak
the peak should reduce because every time I set x equal to ct for any later time, I still have the 1 over t to the 1/2 here. So by setting x equal to ct, I am asking what is the value that it has here or here or here. That value goes down as time goes on, and it's easy to see why, because always the density under this curve must be a constant. It's a probability. So if I'm allowing it to broaden like this, I have to allow it to come down from the center. Yes, this is the probability of finding it at some position x at time t for the drift diffusion equation. And here this probability moves to the right. This is a t equal to 0, this is a t equal to t1, this is a t equal to t2, this is a t equal to t3. So in each of these times, this particle has, the probability distribution is moving to the right, and the position of the peak is c times t1, c times t2, c times t3. It's also broadening in time, and it's broadening by the factor 1 over t to the 1/2 about this point. So it's drifting because it's moving in one direction. It's also diffusing because the distribution is broadening. And in some, it's always symmetric. So look at this function. About this point, it's always symmetric. So it's as though it's sort of moving in its center of mass, but diffusing is symmetrically on both sides. Okay. Okay, so I want to do one particular problem, one or two different problems, which look at the diffusion equation in steady state. And the biological problem that we want to look at is the following. Imagine that I have some cell here. There is some chemical that is being absorbed by, let us say, receptors on the surface of the cell. So the moment a particle comes, a ligand, let us say, comes, attaches to a receptor, it is internalized. These ligands are diffusing around in the space outside the cell, somewhere in the extracellular matrix. Or just if it's bacterium, it's in the fluid in which the bacterium is actually swimming. I want to ask, suppose I know the following. I'm saying very far away, I know that the density, let us say at infinity, is density rho naught. At the surface, the density vanishes, which means that any particle, any ligand that reaches the surface is immediately swallowed up. So it doesn't allow any density at the surface. In steady state, what is the number of particles that is coming and hitting the surface? What is the total current across the surface? Question is total current reaching the surface. Okay. This is a sphere. The sphere has some radius a. Far away, the density is fixed to be infinity. So the system will settle down as you eat up at the sphere these various ligands that are coming in. You have to keep refreshing the density at the outside, at the boundaries. When you refresh it in such a way, the density is always maintained at 0. And we want to ask in steady state for the system, what is the density profile, what is the net current that enters the surface. So then the equation that we have to solve is the diffusion equation, delta rho by delta t equal to d del squared of rho, with the condition that rho is rho naught at distance r going to infinity, and rho equal to 0 at the sphere surface. And I wrote r there. What I mean is I want to take a coordinate system which the sphere is centered at 0. This distance is r, and infinity corresponds to r going to infinity at any point. So, I am solving the diffusion equation for any point r here. As I send r going to infinity, the density must be a constant. If I send r going to the surface or anywhere inside the surface, the density is 0. Because I am looking at steady state, I can say that nothing depends upon time, therefore delta rho by delta t must identically be 0. And this is a consequence of what I will call steady state. Steady state meaning nothing depends upon time. I am always supplying enough ligands from the outside so that the density is maintained at infinity.
We want to find at what rate there should be new ligands so that there are always ligands on the surface.
We can also ask that question, but we want to ask a simpler set of questions. What is the number? If you know the number that are being eaten up as a consequence of crossing the surface, you know what is the rate they have to be replenished. So that's the question that means. So essentially, a lot of questions boil down to the question of how many are being absorbed at the surface, which is a perfect absorber of anything that comes to it.
That we are calculating the drift and diffusion, the sum of those two will be what reaches the surface.
So here there is no drift term because there is no net velocity. The ligands are just wandering around, diffusing at random, and if by chance they happen to hit the surface, then they are immediately eaten up. But there is nothing systematic about how they are moved. There is no net motion. In terms, everything is still diffusive. Okay. So first of all, if we say delta rho by delta t equal to 0, that means we can solve the simpler equation del square of rho equal to 0. Because that is all that survives here, and this should be d times del squared of rho equal to 0, if I set the left hand side equal to 0. Now, del squared, because I have spherical symmetry, I can simplify this. And I can simplify by going from my usual Cartesian coordinates to spherical polar coordinates. Which means that this quantity del squared, which is delta squared by delta x squared plus delta squared by delta y squared plus delta squared by delta z squared, with, if I assume that any function this is operating on is only a function of the radius r, which is square root of x squared plus y squared plus z squared, then assuming radial symmetry, this operator becomes something very simple. It becomes something which looks like 1 over r squared delta by delta r times r squared rho of r squared delta rho by delta r, I think that was, yeah, delta rho r by delta r. This is something that you'll have to go back and look up, and something that you need some practice with if you haven't seen it. Remember that we can describe systems in many ways. We can say, here is the x coordinate, here is the y coordinate, here is the z coordinate. But I can also say, this is a distance r from the origin. It is at a difference theta from the z axis, and if I project it down to the xy plane, then there is an additional angle which I will call phi that tells me where it should be. So x, y and z can be replaced by r, theta and phi, where r is square root of x squared plus y squared plus z squared. If a function is symmetric, has the symmetry of a sphere, spherically symmetric, then all the properties of that function depend only upon r, not on theta and phi. So here x, y, z was mapped onto r, theta and phi, but a function that depends only upon r, although it can look very complicated in terms of x, y and z, looks very simple in terms only of r, because it doesn't involve theta and phi. So because of the way we've set it up, we said this is a sphere at infinity, which is a spherical, which is infinity distance away, that is still, I have fixed the density. It does nothing depends upon theta and phi. Everything depends only upon the factor r. Okay. So then this particular del square term has a simple form. It actually begins to look like this.
How did you apply the operator on it?
I didn't apply it yet. I said this is the del squared operator that we're used to. So what we define in the case of Cartesian coordinates, delta square by delta square, del square, and I would operate this on some function here. Suppose the function, in general I can take this and operate it on any function, but I want to look for some simpler types of functions for which I don't need to use this full complicated operator. Those are functions that are functions not of x, y and z separately in some complicated way, but a function only of the quantity square root of x squared plus y squared plus z squared, which is the radius. It doesn't depend upon any other parts of the function, only depends upon this.
So how did you do the transformation?
I didn't show you the transformation, I just wrote down the final answer, that this becomes this in the case of a function. If I operate this function on this operator on a function that is a function only of r, that is the same as operating this function on a function only of r, on the same function. It's much simpler because now there's only one thing that operates on f of r, whereas here there were three different things, the x, y and z dependencies that I had to operate on this function, and things would look very messy. So I'm looking for answers that are simple, so I want to exploit all the symmetries in the problem, and the symmetries here are radial symmetry.
No, but I'm asking if I had to do this, then I would do dou square by dou x square into under root of x square plus y square plus z square, plus like that I would operate.
You can do it in a much more complicated way, exactly. You can take this function here, suppose f of r, I would write it as f of square root of x squared plus y squared, and whatever it was. For example, this function f of r could be r squared, for example, which would be x squared plus y squared plus z squared. Then I could operate this operator on that and take two derivatives. So one derivative would give me on this function would give me 2x, a second derivative would give me 2. So operating the del squared operator on the r squared factor would give me 2 plus 2 plus 2, which is 6. Okay, so that's one way to do it. But otherwise I can say f of r is a function of r squared. I can do it using this particular method. And you can just verify and see if these answers are the same, to what extent they're the same.
So that is 1 by r square del del r of r square.
1 by r squared delta by delta r of r squared delta rho by delta r. So I mean, well, okay, bad notation, I called it f here, so in this case it should be delta f by delta r. Okay. So now when we go back and put it in our equation for the steady state here, which means we have to solve this particular equation here, what we have is d over r squared delta by delta r of r squared delta rho by delta r must equal 0. Okay. Now this quantity, of course, I just multiply by r squared by d, I can get rid of this because I have 0 on the right hand side. So this implies that delta by delta r of r squared delta rho by delta r equal to 0. Okay. Which implies itself that r squared delta rho by delta r must equal a constant, call it c. See, for the sake of notation, let's call it something else. let's call it alpha for the time being, okay, which means that delta rho by delta r is alpha divided by r squared. I'll just pull this factor down. Which means I can take one more step. Which means that delta rho, rho takes the form alpha divided by r plus a constant. So, let us just check how this works. Take one derivative of this, I get minus 1 by r square. So, I should put a minus alpha there to get the right sign over there to be consistent with this particular sign, plus a constant here. Okay. I can fix all of this because I know that as r becomes very large, the constant must be rho naught. That is the density at infinity. Okay. At r equal to a, this must vanish, because there is no density at the surface. So, therefore, it is very easy to write the final answer. Rho of r is just rho 0 times 1 minus a divided by r, where a is the radius of the sphere. Was this clear? What I did, I solved this differential equation. None of the differential equations that I will solve will be very difficult. They will at most look like this. I first got rid of this term here because this I could always multiply this by r square over d, both left and the right hand side. This will then become 1, this will be 0 on the right, that does not change anything. So, then I reduce it to this particular term here. Now, I must integrate on both sides. When I integrate, I can basically say this becomes r squared delta rho by delta r equal to a constant, because differentiating both sides would give me 0 here and a delta by delta r on this side. Okay. Once I have a constant, I can say delta rho by delta r is constant divided by r squared, no problem doing that. Now, I have to integrate it once more. When I integrate it once more, I get minus alpha by r coming from this factor here, but I also get an additional constant of integration. So, now I have to fix this constant and this constant, I do not know what they are, but I can fix it from the two bits of information that I know. At very large distances, all the way to infinity, the density is a constant. So, at very large distances, 1 by r becomes basically 0. So, I can forget about this, and the density is rho naught. So, that fixes C. At distances at the sphere surface, where r equal to a, the density is 0. So, whenever I substitute r equal to a here, this whole term on the right hand side must vanish. That is ensured if you just put everything back, that if rho of r is rho naught times 1 minus a over r, when I set r equal to a, 1 minus 1 is 0, density is 0. When I set r equal to infinity, density is rho naught. So, if I plot rho of r as a function of r, this is rho naught at infinity, and it vanishes as r becomes a. That is how rho of r behaves. So, now with this, we have managed to solve this particular problem of what is the density profile as a function of r about the cell that has a lot of ligands on it, which just essentially functions as a surface which absorbs anything that falls on it. It's a fully absorbing surface, and we have written an expression of that form.
Regarding that final equation, rho is equal to minus alpha by r plus rho naught, right?
Yes. Yes. Because then C I have fixed by saying C must equal rho naught here.
Now from the how you got this?
This is the same thing, no? Rho of r is rho naught, which is this rho naught factor here. Then we had to fix alpha. We fixed alpha by saying the density vanishes at the sphere surface with radius a. So, if I put a for r here, then rho must be 0. So, minus alpha divided by A plus rho naught must equal 0. Therefore, I can write I can write alpha in terms of rho naught, which is what I have done here.
Why did you draw this curve like this and not like?
Because I know that it is 0 over here and non-zero over here.
Yeah, but why did you make it smooth?
Because I am really essentially plotting this function here. So, I can plot this function directly. I can say I know that it is rho naught far away. As I come closer and closer to this point, it goes to 0. Precisely at this point, if I look at R a little larger than A. Huh?
No, I'm asking why did you draw a slope like this? And it could have been increasing like this and saturate. Why did you make your slope like that?
That is true. That is true. I don't. You can okay. So try and plot it and see.
Okay.
Use MATLAB to try and plot it and see what it should look like. And if we need to correct this, we can correct it. Right now, I just wanted to emphasize the fact that it was 0 here and rho naught here. I was not concentrating so much on the shape of the curve.
So this is related to this rho of R is also a measure of probability.
That's right.
density,
That's right.
And the area must be 1, the total area under the curve.
That's not necessary because they're being density is being eaten up here and supplied here. You keep supplying particles at the boundary to compensate for the fact that the sphere absorbs all of them and then it eats it up.
Or it's not a closed system.
So the total number is a constant, but that is ensured by inserting particles at infinity and letting them being eaten up at the surface of the sphere. Okay. In a sense, you can tell that the density has to be a constant because nothing here depends upon time. If I integrate this over all space, I will get some number, which is the total density. Only I have to be careful that I don't get infinity here because of a factor of rho naught here. So that's because I assume that things are right. At infinity, there is there is some fixed density. So the total number will be infinite, strictly speaking. So it only makes sense to talk about densities, rho of R, and density profiles. Okay. All right. Was there anything more that I had to? Okay. So let me start here the next time, since I'm already a little bit over time. We'll start here the next time and then go on to see how this result is actually useful to us in deciding the efficiency of a cell in absorbing ligands at its surface. Okay. All right.